Hello everyone, welcome to the session on methods of estimation. Before entering into the topic, let us recall some basic terms in statistics. Statistics is a branch of science which deals with planning, collecting, analyzing and interpreting information about a collection of objects under study. The collection of all objects under study is called a population. A representative part of the population is usually called a sample. Suppose a population is having a probability distribution or probability density function with a parameter theta. Sometimes the distribution form is known, but the parameters theta may be unknowns. So, these unknown parameters are to be estimated based on the sample values. This information will provide knowledge about the whole population. There arises the need for estimation from sample values. Suppose we have a random sample x1, x2, etc. xn from a population following PDF denoted by f theta x. This theta is the unknown quantity and it is called the parameter. You have to estimate this theta using the sample. Hence, in brief, estimation methods are very important in any statistical investigation. Sometimes we will use a single value as an estimated value, or sometimes we say that the parameter lies in an interval. These are respectively called point estimation and interval estimation. For example, the mean monthly income of employees in a factory is rupees 30,000. It is point estimation since we have only a single value as the estimate, or we will say that the monthly income is between 27,000 and 32,000. This is interval estimation since the income lies in the interval 27,000 to 32,000. This means if we use capital T of x as a statistic means a function of the sample values. If it is x1 plus x2 plus etc. plus xn by n, it denotes the sample mean, and suppose this small x1 takes the capital X1 takes the value small x1, capital X2 takes the value small x2, etc. Capital Xn takes the value small xn, then small t of x is equal to x1 plus x2 plus etc. plus xn divided by n. Here we use the statistic t of x as an estimator for estimating the population parameter theta, and small t of x is a single value. It is an estimate. This single value is a method of point estimation, and suppose you are getting this t of x as 30,000, then this is our point estimate. Or if we say that it lies in the interval 27,000 to 32,000, then we say that it is interval estimation. Now, let us see more examples involving different types of populations. For the time being, assume that we have sample observations from Poisson distribution. We know the probability mass function of Poisson distribution. So, the probability mass function of the Poisson distribution, let us write it as probability of x is equal to x is equal to e raised to minus lambda, lambda raised to x by x factorial if x is equal to 0, 1, 2, etc. Here the only unknown quantity is lambda and it is the parameter of the Poisson distribution. And also you know that for the Poisson distribution, mean is equal to lambda and variance is also equal to lambda. So, we have to estimate this unknown quantity lambda based on the sample values. Next, let us look at the estimation of the parameter of the Bernoulli distribution with parameter p. The mean of the Bernoulli distribution is p and variance is pq. So, for the Bernoulli distribution, the probability mass function is probability of x is equal to small x is equal to p raised to x into 1 minus p raised to 1 minus x if x is equal to 0, 1. It is the outcome of a coin tossing experiment. What is the probability of getting a success? It is represented in the model. Here the parameter involved is p, which is unknown. Once we get a knowledge about p, we get all the information about the population. We cannot arbitrarily choose the sample mean or sample variance etc. as the estimator. We need a procedure to estimate the unknown parameters of distributions. There are several methods of estimation. We have two well-known methods existing in the literature for this purpose. These are maximal likelihood method and method of moments. We would be concentrating on these two methods during this session. What is this MLE method? As the name indicates, we are maximizing the likelihood function. What do you mean by the likelihood function? If a random sample x1, x2, etc. xn is taken from a PDF f theta x, then the likelihood function is the joint PDF. Hence, the likelihood function L theta x1, x2, etc. xn is equal to the joint PDF of the sample x1, x2, etc. xn, and it is equal to f theta x1 into f theta x2, etc. f theta xn is the product of f theta x1, f theta x2, etc. f theta xn, because these samples are independent and identically distributed. These values f theta x1, f theta x2, etc. f theta xn are calculated at the sample points x1, x2, etc. xn. For given values of x1, x2, etc. xn, the likelihood function is clearly a function of the parameter theta. Now, the value of the theta that maximizes the likelihood function is called the maximum likelihood estimate. Hope you are familiar with the method used in calculus for the maximization of a function. To maximize a function of one variable, we put df of x by dx is equal to 0, solve for x and check the sign of the second derivative d square f of x by dx square at this point. That means, if we have a function f of x of one variable x, we find the first derivative dfx by dx and the second derivative d square fx by dx square. By putting dfx by dx is equal to 0, we get the maximum or minimum point solving that equation, and substitute that value in the second derivative d square fx by dx square. If it is negative, there occurs the maximum, and if it is positive, there is the minimum. But if we have a function of more than one variables, we use the partial derivatives. In the MLE method, we have to maximize the likelihood function. Use the above described method and identify the maximum point. So, in the case of likelihood function, we have L of theta x1, x2, etc., xn. In the method of maximal likelihood, we have to maximize this likelihood function. It can be a function of more than one parameters. So, we need the partial derivatives, first order partial derivative and second order partial derivatives. Suppose we have to find out the maximum of the likelihood function at the point theta. That means, we have to find out the maximum likelihood estimator of the parameter theta. So, we find partial derivative of the logarithm of L theta x1, x2, etc., xn with respect to theta, and also the second derivative dou square log L theta x1, x2, etc., xn with respect to theta. Here we are taking the log likelihood function, because maximizing the likelihood function will be same as maximizing the log likelihood function, and sometimes it is easier to use the log likelihood function. So, by putting dou log L by dou theta is equal to 0 and solving for theta, we get the maximum or minimum point, and check the sign of the second derivative. At that point, if it is less than 0, it is a maximum point. If it is greater than 0, it is a minimum point. So, we have described the maximal likelihood estimation method. Let us use this method in some non-distributions. Consider a simple example which we observed in the beginning of this talk. Which was that PDF? Yes, it is our Bernoulli distribution with parameter p. So, let us take a random sample from the distribution. Let it be x1, x2, etc., xn. So, for the Bernoulli distribution, probability of x is equal to x, or the probability mass function is p raised to x into 1 minus p raised to 1 minus x, where x is equal to 0, 1. To estimate the parameter p, we need the likelihood function. Let us write down the likelihood function L of, since the parameter is p, I shall write p here, then the sample values x1, x2, etc., xn, since we have taken a random sample from the Bernoulli distribution, and this will be equal to the product of the probability mass function at the sample points. So, p raised to x1 into 1 minus p raised to 1 minus x1 into p raised to x2 into 1 minus p raised to 1 minus x2, etc., p raised to xn into 1 minus p raised to 1 minus xn. This is equal to combining the terms with same bases. So, we have p raised to x1, p raised to x2, etc., p raised to xn, we get p raised to summation I is equal to 1 to n xi. Again we have 1 minus p raised to 1 minus x1, 1 minus p raised to 1 minus x2, etc., 1 minus p raised to 1 minus xn. So, combining those terms, we get 1 minus p raised to 1 minus x1 plus 1 minus x2 plus etc., plus 1 minus xn. So, it means n minus summation I is equal to 1 to n xi. So, this is the likelihood function. Now, let us take the logarithm of the likelihood function. So, log L p x1 x2 etc. xn is equal to, when you take the logarithm of the right hand side, it is of the form logarithm of x raised to m. We know that it is equal to m log x. Therefore, we get this is equal to summation I is equal to 1 to n xi into log p plus n minus summation I is equal to 1 to n xi into log 1 minus p. Now, we have to find out the first order derivative of the log likelihood function with respect to p. So, since we have only one parameter, d log L p x1 x2 etc. xn by dp. That means, the first order derivative of the log likelihood function with respect to p, this is equal to, now look at the first term in the right hand side, it is summation I is equal to 1 to n xi into derivative of log p, it is equal to 1 by p plus, now in the second term we have n minus summation I is equal to 1 to n xi into derivative of log 1 minus p, and it is 1 by 1 minus p into minus 1. So, this is exactly equal to summation I is equal to 1 to n xi divided by p plus n minus summation I is equal to 1 to n xi into minus 1 divided by p. So, we can write instead of plus here negative symbol, and this is n minus summation xi divided by 1 minus p. Now, the method is you have to equate the first order derivative to 0. So, putting this is equal to 0 and solving for p, we get summation xi into 1 minus p minus n minus summation I is equal to 1 to n xi into p divided by p into 1 minus p is equal to 0. Now, we have a fraction which is equal to 0. So, the numerator will be equal to 0. Simplifying the numerator, we get summation I is equal to 1 to n xi minus p into summation I is equal to 1 to n xi minus n into p plus summation I is equal to 1 to n xi into p is equal to 0. These two terms are cancelled and we get summation I is equal to 1 to n xi minus np is equal to 0. This implies p is equal to summation I is equal to 1 to n xi divided by n. This is an estimator of the parameter p and we can put this as p hat. Now, we cannot say that it is the maximal likelihood estimator. We got the point at which the maximum or minimum of the log likelihood function or the likelihood function exists. Now, let us check whether the second order derivative is less than 0. So, we got p hat is equal to summation I is equal to 1 to n xi divided by n, or we can write it as x bar, our sample mean. Taking the second derivative, d square log L p x1 x2 etc. xn with respect to p, this is equal to summation I is equal to 1 to n xi into derivative of 1 by p. It is derivative of 1 by p means derivative of p raised to minus 1, and you know that the derivative is minus 1 into p raised to minus 2, or this is minus 1 by p square. And similarly, the derivative of the second term with respect to p, it is minus n minus summation I is equal to 1 to n xi into derivative of 1 minus p, it is minus 1 by 1 minus p all square into derivative of minus p, it is minus 1. So, simplifying again, taking the negative symbol outside, it is minus of summation I is equal to 1 to n xi divided by p square. Here we have one negative sign and again two negative signs. So, this term is plus n minus summation I is equal to 1 to n xi divided by 1 minus p all square. Now, you can see that this is less than 0 since the terms in the bracket is always positive, and hence the second order derivative is less than 0 at the point p hat is equal to x bar. Thus, we got a maximum likelihood estimator of the parameter p of the Bernoulli distribution. Let us consider another example of a random sample from binomial distribution. The binomial distribution with parameters capital N and p. I have taken capital N as parameter to distinguish from the sample size n. So, the random sample x1, x2 etc. xn is taken from the binomial distribution with parameters capital N and p. Hence, the density function or the probability mass function is probability of P x is equal to n C x p raised to x 1 minus p raised to n minus x. Here we are using capital N as one parameter. So, this is capital N minus x if x is equal to 0, 1, etc. up to n. Now, assume that capital N is fixed. Then the likelihood function L of p x1, x2, etc. xn is equal to NCx1 p raised to x1 1 minus p raised to n minus x1 into NCx2 p raised to x2 into 1 minus p raised to n minus x2 etc. NCxn p raised to xn into 1 minus p raised to n minus xn. This can be simplified into NCx1, NCx2, etc. NCxn into p raised to, now p raised to x1, p raised to x2, etc. p raised to xn. So, it is p raised to summation I is equal to 1 to n xi. Again we have 1 minus p raised to n minus x1 into 1 minus p raised to n minus x2 etc. 1 minus p raised to n minus xn, and it is small n into capital N minus summation I is equal to 1 to n xi. This is the likelihood function. Let us take the logarithm of this likelihood function, and hence log L p x1, x2, etc. xn is equal to logarithm of NCx1 into NCx2, etc. NCxn, and it is the logarithm of product. So, we can write it as logarithm of NCx1 plus logarithm of NCx2 plus etc. plus logarithm of NCxn, again plus we have logarithm of p raised to summation xi, it is summation I is equal to 1 to n xi into logarithm of p, then we have logarithm of 1 minus p raised to nn minus summation xi, it is plus nn minus summation I is equal to 1 to n xi into logarithm of one minus p. Here we have the parameter p, you have to estimate the parameter p. So, we have to find out the derivative with respect to p, hence again the derivative with respect to p is d log L p x1, x2, etc. xn with respect to p, dp is equal to, in the first term there is no p, here also we have no p. Therefore, when you take the derivative with respect to p, these terms is exactly equal to 0. So, here we have the derivative summation I is equal to 1 to n x I into derivative of log p, it is 1 by p plus n n minus summation I is equal to 1 to n x I into derivative of log 1 minus p, it is 1 by 1 minus p into minus 1. Therefore, this is equal to summation I is equal to 1 to n x I divided by p plus, again we have negative symbol. So, it is minus n n minus summation I is equal to 1 to n x I divided by 1 minus p. Putting this is equal to 0 and solving, we get summation I is equal to 1 to n x I into 1 minus p, taking the LCM, minus n n minus summation I is equal to 1 to n x I divided by p into 1 minus p is equal to 0. Solving this, we get summation I is equal to 1 to n x I minus p into summation I is equal to 1 to n x I minus n n into capital N plus summation I is equal to 1 to n x I. Here we have one p, since we are taking the LCM. So, minus n n into p plus summation I is equal to 1 to n x I into p is equal to 0. Again these two terms are cancelled and we get p hat is equal to summation I is equal to 1 to n x I divided by n into capital N. It is exactly equal to x bar divided by capital N. So, the maximum of the likelihood function or the log likelihood function we have to find out. The point which we get by solving the derivative of the log likelihood function is x bar by n. Now, you have to check whether it is a maximum point or the minimum point. So, we need the second derivative. P hat is equal to x bar divided by capital N. Here we have the first order derivative. Take the second order derivative, d square log L p x1 x2 etc. xn with respect to p dp square. This is equal to, taking the second derivative, summation I is equal to 1 to n x I into minus 1 by p square, derivative of this one minus n n minus summation I is equal to 1 to n x I into derivative of 1 by 1 minus p, it is minus 1 by 1 minus p square into minus 1. And we can write this as minus of summation I is equal to 1 to n x I divided by p square plus n n minus summation I is equal to 1 to n x I divided by 1 minus p all square. Again, the term within the bracket is always positive and hence this will be less than 0 at the point p hat is equal to x bar by n. Therefore, the maximum likelihood estimator of p is p hat is equal to x bar by n. This is the maximum likelihood estimator. Now, let us consider the Poisson distribution. So, we take a random sample from the Poisson distribution with parameter lambda, and the probability mass function of the Poisson distribution is probability of x is equal to small x is equal to e raised to minus lambda, lambda raised to x by x factorial, where x is equal to 0, 1, 2, etc. Here lambda is the unknown parameter. You have to estimate that parameter using the maximum likelihood estimation method. Taking the random sample x1, x2, etc., xn from this probability density function or probability mass function, we get the likelihood function as, since lambda is the parameter, we write lambda here. It is lambda x1, x2, etc., xn is equal to e raised to minus lambda, lambda raised to x1 by x1 factorial into e raised to minus lambda, lambda raised to x2 divided by x2 factorial, etc., e raised to minus lambda, lambda raised to xn by xn factorial. This is equal to, again combining the terms with same basis, it is e raised to minus lambda into e raised to minus lambda, etc., up to e raised to minus lambda n times. So, it is e raised to minus n lambda into lambda raised to x1 plus x2 plus etc. plus xn. So, lambda raised to summation I is equal to 1 to n xi divided by x1 factorial, x2 factorial, etc., xn factorial. Taking the log likelihood function, we have log L lambda x1, x2, etc., xn is equal to logarithm of e raised to minus n lambda, it is minus n lambda, plus logarithm of lambda raised to summation xi. So, it is summation I is equal to 1 to n xi into log lambda divided by logarithm of x1 factorial, x2 factorial, etc., xn factorial. So, we can write it as minus logarithm of x1 factorial, x2 factorial, etc., xn factorial. Again, put the first order derivative with respect to lambda is equal to 0. So, we have d log L lambda x1, x2, etc., xn d lambda. This is equal to, finding the derivative with respect to lambda, it is minus n plus summation I is equal to 1 to n xi into derivative of log lambda, it is 1 by lambda, derivative of logarithm of x1 factorial, x2 factorial, etc., xn factorial with respect to lambda is 0. So, this first order derivative is equal to 0 implies n is equal to summation I is equal to 1 to n xi divided by lambda, and hence lambda hat is equal to summation I is equal to 1 to n xi divided by n, and it is our sample mean x bar. Now, check the sign of the second order derivative. Here d square log L by d lambda square, d square log L d lambda square is equal to, here we have this term is not containing the term or the parameter lambda. So, derivative is 0. The second term we have summation I is equal to 1 to n xi into derivative of 1 by lambda, it is minus 1 by lambda square, and this is always less than 0 when lambda is equal to x bar, and hence the maximum likelihood estimator lambda hat is equal to the sample mean x bar for the parameter of the Poisson distribution. Consider a random sample from the uniform distribution. In this case, usual calculus method does not work. Let us consider a random sample from the uniform distribution with parameter theta and with density function f of theta x is equal to 1 by theta if 0 less than x less than theta and 0 otherwise. So, in this case, how can we find out the maximum likelihood estimator? The likelihood function in this case is L theta x1, x2, etc., xn is equal to 1 by theta into 1 by theta into etc. up to 1 by theta n times. So, it is 1 by theta whole raised to n if the sample values are between 0 and theta. So, if 0 less than x1, x2, etc., xn less than theta and 0 otherwise. The likelihood function is 1 by theta raised to n if 0 less than x1, x2, etc., xn less than theta and 0 otherwise. Now, you have to maximize the likelihood function with respect to theta. You can see that the likelihood function takes only two values, 1 by theta raised to n and 0. So, the maximum value of the likelihood function is 1 by theta raised to n. The maximum of this function occurs when theta is minimum. Therefore, the likelihood function can be written as L theta x1, x2, etc., xn is equal to 1 by theta raised to n if 0 less than x1, x2, etc., xn is greater than 0 means 0 less than minimum of x1, x2, etc., xn, which is less than or equal to maximum of x1, x2, etc. xn less than theta, 0 otherwise. As I told earlier, the likelihood function is maximized when theta is minimum. From the right hand side of this inequality, we can see that theta is greater than maximum of x1, x2, etc. xn. Therefore, the minimum value of theta is maximum of x1, x2, etc. xn, or we can write it as maximum of xi. Hence, the maximum likelihood estimator is maximum of xi in the case of uniform 0 theta. Now, let us consider another example from the uniform distribution with PDF f theta x is equal to 1 if theta less than x less than theta plus 1, 0 otherwise. Again, you are taking a random sample from this population and you have to find out the maximum likelihood estimator of the parameter theta. Then the likelihood function is L theta x1, x2, etc. xn is equal to 1 into 1 into 1 n times. So, it is 1 if all the sample values x1, x2, etc. xn are between theta and theta plus 1, 0 otherwise. Therefore, this is equal to 1 if theta less than minimum of xi or minimum of x1, x2, etc. xn less than or equal to maximum of xi or maximum of x1, x2, etc. xn less than theta plus 1 and 0 otherwise. Here also the maximum value of the likelihood function is 1 if all the sample values are between theta and theta plus 1. Hence, the maximum likelihood estimator in this case is, from this inequality we can write minimum of xi greater than theta, which is greater than maximum of xi minus 1 or maximum of xi minus 1 less than theta less than minimum of xi. Hence, any statistic taking the value between maximum of xi minus 1 and minimum of xi is a maximum likelihood estimator. It means that maximum likelihood estimator may not be unique. Similarly, we can consider another example from the uniform distribution itself with PDF f of theta x is equal to 1 if theta minus 1 by 2 less than x less than theta plus 1 by 2, 0 otherwise. the likelihood function is again 1 if theta minus 1 by 2 less than x1, x2, etc., xn less than theta plus 1 by 2, or this is 1 if theta minus 1 by 2 less than minimum of xi less than or equal to maximum of xi less than theta plus 1 by 2, 0 otherwise. The likelihood function is maximum, that means it takes the value 1 if theta minus 1 by 2 less than minimum of xi less than or equal to maximum of xi less than theta plus 1 by 2. Therefore, theta is less than, from the left hand side of this inequality, theta is less than minimum of xi plus 1 by 2, and from here we have theta is greater than maximum of xi minus 1 by 2. It means that if theta is between these two values, the likelihood function will be maximum. Therefore, any statistic between maximum of xi minus 1 by 2 and minimum of xi plus 1 by 2 is a maximum likelihood estimator. Thus, we came to the end of this session. Hope you enjoyed it. Thank you very much.